Hey everyone, welcome to 197 Concepts. In this video, I'm going to tell you how to add n numbers and different numbers in the software MASM. Okay, so without any delay, let's start our tutorial. And as you can see here on the screen, you will be able to see the program code that we are going to use in order to add n numbers. Now, this n numbers, I'm assuming that there are a total of 8 numbers. Okay, so if this is, you can add any numbers, but I'm going to limit my numbers as 8, and those 8 numbers are taken here, their corresponding their respective hexadecimal values and the final result after adding each value and the representation of the result in hexadecimal. Okay, so here this 99 number represents the hexadecimal value, and the 99 is equals to 153 in the decimal numbering system. Now, if you add these two, you are going to get 305, which is again represented in hexadecimal as 131. For much clarification, I'm going to place H, okay, for hexadecimal numbers. I'm going to place H for hexadecimal numbers and D for representing the decimal numbers. Okay. So the MASM can take hexadecimal values and the decimal values also, but be careful, you have to mention this H or D. For example, if I've mentioned here 8H, that means the value of 8 in hexadecimal when converted to the decimal is again 8. Now, if you want a clarification, if I type the value 153 beside alongside with the value of t with the character d, then the MASM is going to take that particular value as 99, because it's going to convert 153 into hexadecimal numbering representation, and that exactly that value, the 153 value, will be represented as 99 in hexadecimal numbering system. Why is it done that? There's another video, you can check that out. So here I'm going to add n numbers, and those numbers, hexadecimal numbers. So those 8 hexadecimal numbers are represented here, 8 or 7. How many are there? 1, 2, 3, 4, 5, 6, 7. Okay, I've taken one extra count, no problem for that. So I'm going to add these 7 hexadecimal numbering system. So now we come to the program. The first line, assume CS colon code. This tells us that this is not this from when we come to the program, the very first line is assume CS colon code. So this tells the program that wherever you get the code, the label name code, that particular segment of that program has to be stored into the code memory of the 8086. Now the code segment is going to start from here. Since I have typed the name code, all this up to the code ends. Okay, so this whole section is going to be stored in the code segment memory of the 8086. Since we are talking about microprocessor, it's going to store in 8086 segment memory, code segment memory, and the label start defines that my main program is going to start from here. Okay, so the very first line in the main program, the starting of the main program, starting line of the program is move source index comma 4000 h. So my source index is another kind of memory, that is a segment memory, or you can say it as a index memory that is used in 8086 microprocessor. It is built in. So that source index value will be loaded with the 4000 h. Now what is this 4000 h? 4000H is a random location of the memory in 8086 processor. So the segmentation of the memory is different, whereas this memory is different. You can say this as RAM and this as ROM in order to justify. It can be reversible. This can be RAM, this can be ROM, or this can be RAM and can be ROM. So I have shifted there. So it's just that this is data memory. Okay, To be more specific in our terms, in the terms of 8086, this is data memory, and this is the memory that is segmented, that is used by the processor in order to execute the commands. This is not accessible by the user. This is accessible by the user. You can see what is happening in this particular memory. You can access it up to a certain limit, up to a restricted limitation, but you cannot manipulate it, you cannot change it, you cannot do anything other than just giving some values and all. So we will see that in our program when we are executing the program. The next line is CL. Okay, move CL comma 08H. So CL is nothing but your count register CX, the lower byte of CX, which is going to be loaded with the value 08, and the higher byte of accumulator register is I'm going to load it with 00H. This is just my confirmation. This is not necessary line because initially it will be 0, but to be more precautious, to be uh, more accurate, or you can say it not to make any mistakes, because sometimes when you execute the last program there will be some values that will be stuck in the 8086 memory. In order to eliminate such kind of errors, I am initializing AH, the higher byte of accumulator register, with 00H, and from here on our program starts. So for that, let us take an array. So I will explain it with the help of array. So these values, these 99H, 99H space 98H. Since these are all hexadecimal representation, I'm just eliminating that H representation. Okay, 98 space 96 space comma 95 comma 97 comma 92 comma 90. Okay, so this is the value that I will be typing, or that I will be storing in the data segment 4000H, data location 4000H. This All these values one by one will be loaded into the source index. How is that possible? See, since this is stored in the form of an array, you can say that this is the zeroth element, this is the first element, second, third, fourth, fifth, sixth. Okay, if I need to call only a specific element, let us say if I need to call the fifth element, then 0, 1, 2, 3, 4, 5. 92 is the fifth element. How is it accessed? With the help of index values. You can call it as, if this array is given the name A, capital A, or small a, whatever you wish. So I'm going with capital A. Then A of 0 is equals to 99. Whereas I'm going to copy this 98, 96, 95, 97, 92, 90. Okay. So these are going to be changed.
The numbers 99, 98, 96, 95, 97, 92, and 90, all these six numbers, all the seven numbers are represented in the form of array, or you can say that these will be stored in the form of an array in this manner. Now if I need the fifth element, so I will be counting 0, 1, 2, 3, 4, 5. So a of 5, if this array name or array is assigned to a variable a, then the fifth element can be accessed. The 90, number 19 is a fifth element, and it can be accessed via the value, or by typing the index value a of 5. So in this way, I'm going to calculate, I'm going to add, I'm going to calculate the summation of all these numbers. So for that, my idea is, first of all, I'm going to load the zeroth value into the accumulator register. Then, since already this is loaded in the accumulator register, I'm going to add the value this with this value by just saying that, by just telling the index, source index, to update its index value from 0 to 1. That's what I'm doing here. Okay, so if you go in the stepwise manner, I'm loading 00H into the higher byte of accumulator register. Then I'm loading source index, the value of source index, the first value of source index into the lower byte of accumulator register. Since the accumulator register, lower byte of accumulator register is already loaded with the first value, 0th value, it should be added with the first value. That's what I'm doing. I'm typing in the add command. Okay, so AL is the first value that I have to add, and the second value is previous value plus 1. So previous value plus 1 means initially the source index is pointing towards this 0th value. Now what I'm doing, I'm not typing here SI, I'm typing SI plus 1. That means 0 plus 1, which is source index, which tells that the source index must be pointing towards this value, and this value will be added to the value that is present in the accumulator register, which is nothing but the 99. Okay, after adding those two values, we get a summation of 152 in decimal numbering system, which will be represented as 131H. So these are a little bit up and down. Let me do those correctly. Yeah. So 305 is a decimal value. If you add 152 and 153, you get a value of 305, 305. But that 305 is represented as 131 in the hexadecimal MASM values. And then what we are going to do is we are going to add the carry. So you're going to use the command ADC to add 00H into the higher byte of accumulator register. This is because for some situations when you're going to cross the 8 bits, that is when you're going to obtain, or when you're going to access the 8th bit, in that time, since you're using only the lower byte of accumulator register, it is restricted to 0 to 7 bits, that is a total of 8 bits. When you're exceeding this 8 bits, definitely you're going to get a carry. So this carry has to be loaded. For example, if you take here 152, that is 99 and 98H, whenever you are going to add this, definitely it is going to increase. It is going to increase from 2 bits to 2 digits to 3 digits. That's what you are going to get 131. But initially 99 and 98, when these two are added, you will get only 31H, where this 1 will be stored. This 100th position 1, it will be stored in the carry flag. In order to carry that flag, in order to add that carry flag, you are going to use this command. So this will be more clearly understandable while executing the program. And since the source index execution is not completed, I have just added these two elements. I need to add this third element also. For that, what I'm going to do is I'm going to just increment the source index value from 4000 to 4001. That means initially it was pointing at 99. Now it is going to point the initial value as 98. Okay, so this 98 will be stored, not the 98, the summation of 98 and 99, that is 131, will be initially stored into the lower byte of accumulator register, and to that value I am going to add the next value, that is the 96 one. How is this possible? Because my source index, after the increment of its value, that means after adding the carry flag, after adding the carry into the higher byte of accumulator register, I am by default incrementing the source index value from 4000 to 4001. So that's why the source index will be pointing 98 at the base value, and I'm not loading this 98 into the accumulator register because the 98 is already added with 99 and I have got the summation value as 131. I need this value. I need the second element that is present in variable A. So that is why I am going to add the value, source index value. Definitely I'm going to add the source index value, but not the pointing one. I'm going to add the value that is present at +1 position of the initial source index value. So after incrementing, so what will be the source index pointing is 98 value, but I'm not going to add that as it is already added to the previous value. I'm going to add 96 with the summation 131. Okay, so that is why. How is it possible? So source index will be pointing from initially source index. So when we are going to start the program, it is initially pointing at 0. Okay, then after incrementing, it is pointing at 1. but here it is si plus 1. So si value is 1 plus 1, that means 2. Si of 2, now si of 2 is 96, that means a of 2. Okay, a of 2, I have typed the values here a little bit mistake, so actually it's not 96, the second value is 98. I have missed that particular value. This is 96, then this is 95, then this is 97, then this is 92, then this is 97, 92, and this is finally 90. So let me check the values again. 99, 98, 96, 95, 97, 92, 90. Okay, so initially it was pointing at this value, and I'm going to add this value and this value. Since it is si plus 1, 0 plus 1, so 99 plus 98. Now I'm pointing, after the completion of that summation, I'm pointing at 98, a of 1, I'm pointing at 98, but I'm going to add si plus 1, that is the value at present at the second position, so 96. This will be added. After adding this, again we are going to add the carry flag in order to shift the higher order byte values, because uh, if you speak generally, 99 plus 1 is 100. That means you are going to increase the value, you are going to add the carry that is present at the last into the 100th position. In order to carry out that, you are going to get this. So it will be easily understandable when you are executing the program. So that's the idea, and this incrementation will be carried out until the control cl flag, the cl register 0, it becomes 0. That, if you observe, I have not typed that anyway. That is possible with the help of loop. So loop, by default, when you are going to use the command loop followed by a label, so your function, your program is going back to it is going to jump back to this label that is here. Okay, no doubt in that. But along with this, the program is going to decrement the value of count register by itself. You don't have to specifically type decrement cl or dl. If you are executing the loop function, definitely by default the program is going to decrement this value. Okay, that's a built-in function. So now let us check this, and this code ends and end start tells the end of the program. So I've already typed this code in dos box and it is ready to be shown. So I'm just opening dos box x, and the for base commands. So first of all, clear screen, then next I'm going to mount c colon backslash enter. Okay, then next I'm changing to c drive, and I'm going to change it to the folder 8086, and I'm going to open the edit window. Let me shift to the control F11 full screen mode. Okay, I have to, no, I have to do that here. Okay, yeah, this is the shortcut. Now I'm going to press edit, and what I'm going to do is I'm going to open the already typed program. That name I have given is add n.asm. So this is the program, addition of n numbers, code segments, code segment start si 4000, all the program, complete program. Okay, now this has to be executed. Since I've already typed it, if you're typing program, after typing it, go to save or save as. If it is first time, type press save as, and save it in a particular location. Since I've already typed it, I have not made any changes, but still I'm going to save it. Then add file, exit, and I'm typing the command MASM add n.asm semicolon, no errors. Now link add n.obj semicolon. Okay, af debug add n.exe. So this is our program. Now in this, first of all, you have to load the data into the data segment of the 8086. For that, you have to move towards the section 1 or section 2. Both are showing data segment, right? So both are same. Either you can place your data by using section 1 or by using section 2, no doubt. Now the main thing is how to access those two sections. If you observe at the bottom of the screen, at 7, there are some numbers 1 2 3 4 5 6 7 8 9 and 0, whereas the 6 is blank. Just leave that. You have to observe from 7 8 9 and 0. So 0 is nothing but your function key 10. So these values 1 2 3 4 will represent the f1 f2 f3 f4 f5 f6 f7 f8 f9 and f10. That is the function keys of your keyboard. Now if you see the last key, that is 0, that means when I press F10, the cursor that is blinking at command has to move towards the first section. That is, it has to move towards the right of the screen. Now let us see. So I've pressed the F10 key and it is definitely blinking. The cursor is blinking at DS, that is in section 1. If I want to go down, I have to press F8. So it has came at that bottom section. Now if I want to go left, F9. So it is at section 2. Now see here, I'm going to have just press an arrow, right arrow, and I'm typing here the address 4000. Okay, so initially at the starting values it has done some calculations and it has stored some values, but as you have typed 4000, it is completely zero because in the memory segment you have not typed anything, or the system has not the system is not having any informations to store at that particular location. Now the same thing I'm going to do at is section 1. For that I have to go right and up, or else up and right. So I'm going to right and then I'm going to press the F7 key in order to go up. So DS right arrow 4000. Okay, now observe here, whenever I'm going to type here, that data is going to be shifted here. Oh, I forgot the values. What were those? Let me check those one. So I've taken a photo and I'm going to type the values here. So these are nothing, just to type the numbers, those will be taken out. The first value is 99, then 98, then 96, then 95, 97, 92 and 90. I'm leaving the last value. It's up to 6 and what we have initiated CL as 08. Okay, no problem. If since it is 0, it's even if we add, nothing will happen. I need to come back towards the command value. So for that I'm going to press the F9 key in the keyboard. Now from here on I'm going to execute the program in the step-by-step manner by pressing the function key F1. So first command is moving 4000 into the source index. Now observe the source index value at the topmost of the screen, that is 0000. When I execute this command, it's going to be 4000. That means the values 99, 98, 96, 95, 97, 92, 90, those are already loaded into the source index value, and the source index is already started pointing towards the zeroth element, which is the 99. Now the cx is something, it's 12, and I'm going to load it with 8. Okay, and ah, it's already 0, so it's not going to show any effect, but if you are having some other value, it will be shifted back to 0 or reset to 0. From here on, the main logic starts. So the first element 99 has to be loaded into the lower byte of the accumulator registered. If I press F1, it has loaded. As you can observe, AX. Keep an eye on AX. Keep an eye on the carry flag from the flag registers. Keep an eye on source index. Those three are the registers, and along with the CX, those four registers we are going to observe, and we are going to find out the result. So there won't be any change in the data segment, there won't be any change in the values of data segments. You are just going to observe the change in the AX register. So I believe it would be much easier if I'm having a small screen, because yeah, I can keep it in this way and I can show you the values simultaneously. I can use the mouse and I can show you the values simultaneously, hexadecimal and decimal numbering system. So observe these two, 99. So 99, so I'm adding 153. Let me resize this. Right, these are not, this is not resizable, this is much better, I believe. Okay, so 99 I've loaded in accumulator register, and now I'm going to load the value, the second element, that is with the command si plus 1. So initially it is pointing towards this value. Now I'm saying move one position forward and load this value, not load, add this value with the value that is present in accumulator register's lower byte. So that is 99. See, when I press F1, this is going to shift to 131H, not 131H. It's going to change to 31H, right? I need here full screen, as you have to observe the CS flag also, CF flag also, that's at the left right side of the screen. Okay, rightmost side of the screen. So say right now it is 0. When I press F1, it has shifted to 1. It has changed to the logic state 1. So 98 plus 99 is equals to 131. In hexadecimal, I'm talking about hexadecimal values. Okay, even if you add 98 and 99 in a decimal numbering system, you will get 31. Since we are having only, we are only using lower bytes, it is not showing 131, it is showing only 31. So where that one come from? uh, or you can say in this way, that the 99 and 98 both take only 8 bits, so the resultant will be 8 bits, but the actual value is it's a total of 12 bits. That extra additional 4 bits will come from the carry flag. So that is why we are using this command adc ah, 00. क्या दीदी, आता हूँ एक 5 मिनट. So if you load that, you're going to get, so the command basically adc means add carry flag. Okay, so it basically means add carry flag with some specific value. That specific value here I'm going to take it 00, because any other value is going to be change the higher order value. Okay, done. Now finally I have to increment source index. Since it is as 4000, I'm going to increment it to 4001. Now the program is pointing towards the value 98 instead of 99. And observe CX here, it is at 8. Now when I press F1, it's going back to the address location 0009, and it's going to decrement the CX value by 1. So it's the program has came to 009, and the CX value has reduced to 1. Now I need the windowed value, windowed representation, and here you can see that the accumulator register is at 131, and when you add 99 and 98, you get 131. So this 131 in decimal is 305, as you are adding 153 and 152. Okay, so that's a huge difference. That's a huge uh, representation difference between the hexadecimal and the decimal numbers. Okay, so now I'm going to continue this. Observe carry flag, observe source index, observe AX and CX values. So CX is 7, it's going to run again 7 times. Again I'm going to add AL is having already 131. I'm going to add not 96, not 98, I'm going to add 96, because source index is 1, but here I'm adding source index position, that is 1 plus 1. So 96 is going to add, and see the value will be C7. And since the carry flag is 0, it's going to stay at 1C7. So again, I'm going to increment 4002. And since there is some value in CX register, count register, it's going back to the loop. So this goes on. So 197 will again, 1C7 will be changed to 25C. So since the carry flag is already there, uh, add will only update the lower 8 bits. This adc command, add with carry, will change the higher byte of the accumulator register. Finally we get 25C. Then Again I'm going to increment source index, and again I'm going to loop it since there is some value in CX register. Now since source index is 3, so 3 plus 1 4, 497 will be added with the value 25C, and you should get a result of 2F3. Okay, so F3, and there is no carry flag, so there is no activation of carry flag, that's why you get 2F3. F1, incrementing it to the fourth position, again going to the loop, and same the process is repeated. So this goes on until the last loop, the last iteration of CX. This is the last iteration. After completion of this, definitely the loop is going to be reduced, and since CX value is 0, it should end the program there, but the program is not finishing, the program is not ending itself. That's because I made a small mistake, wantedly I made a small mistake, that is a edit add n.asm. So here at the last of the program, I have not typed the value, not typed the command int03h. So this is the breakpoint. This is the, yes, I want to save it. This is the command that adds the breakpoint to your program. So again, you have to do all the functions, add, you have to type all the commands, add n.asm semicolon, then link add n.obj semicolon, and af debug add n.exe. Now I'm just going to hold F1, as we know all the process. Yeah, this is the end of the CX value. See here, I have incremented the SI value, source index value, to the last value, and I have came to the last iteration of the loop. So CX is having some value 1. When I press F1, that's going to be 0. But instead of going to the upper position or something else, the program has came to int03h. Now from here on, if I press F1, there is no execution. Even all the registers become 0 except the source index. So that's what this command does. If it was not there, it was going to enter into these lines. So add bx plus si comma al. So this is an infinite loop. So this does not end the program. This specific line does that, finish the program. So that's a small thing, and so that's all about addition. Similarly, in the same manner, I'm going to do the subtraction of the subtraction of the numbers. So here are the numbers and their particular representations. Yeah, you might get confused. H, 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 H. This is decimal representation, decimal D, 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 right? And again, this is D, 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 D. And this is H, 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 H. Okay. So a quick recap, even this I've typed it before. I'm just going to do a quick what we say, quick review of the execution. So edit, add, open, subn.asm. So this is the subtraction program of n numbers. So this is already typed in. I'm going to just save it once. Exit MASM subn.asm. So I'm having two errors in the 13th line and the 19th line. So if I'm having such errors, I can just edit that specific program. So observe 13th and 19th line. So expected instruction or directive at 13th and 19th line, open parenthesis or bracket. So where is the 19th line? End start. Code ends end start. Yeah, that's good. Where is the 13th line? Okay, so I've rectified the error. The error was nothing. just at the end start line, when you go towards the right side of the screen, somewhere at column 60 or 70, there was a special character, not a special character, an extra character, which was not understandable by the MASM software, and I have removed that now. And since I've removed it, so it's the same program as the addition of n numbers. It's just that instead of add, we are using this command sub, and instead of add with carry, we are using the command subtract with borrow. Okay, so this tells that whenever you are getting a carry flag as logic 1, subtract 1 from the higher byte of the accumulator register. So I'm going to execute this, so just save this one. Okay, I've pressed a new exit, and we are going in our regular manner, sub n dot asm semicolon, no errors. Then I'm going to link the value, link the file subn dot obj semicolon, and af debug subn dot exe. So this is execution of the subtraction of n numbers. Now first thing what I have to do is I have to go towards the first section and data segment at 4000 location, and what I have to do is I have to load the values. The values which I'm loading are here. So 95, 05, 30, 02, 03, 05. I'm taking 8 values, so no problem for that. I will be stopping till here. So 95, 5, 30, 2, 3. So 2 extra repetitions, no problem. You can keep the values there. So let's go with some other values like say 01 and 01 for better understanding and execution of the program. So first SI will be loaded with, yeah, I have this one also, right? Down means F8, F8 and F9. So DS 4000, you get the values. Up F7, yeah, F8, F8. Now F1. So source index is loaded with the values 95, 5, 30, 2, 3, 5, 0, 1, 0, 1. Now CL is loaded with 08 and AH is loaded with 01. Now the first value 95 will be loaded in accumulator register, and this will be subtracted with the value 5. So 90 minus 5, I'm talking in terms of hexadecimal, you can see the values here. So the accumulator register will be 90. Since the carry flag is 0, there is no change in the higher order byte of accumulator register. Now increment SI, so it's going to be 4001 and it's pointing at 5, but the result is already 90. So 90 minus 5, not 90 minus 5, I'm going to do 90 minus 30, as the 5 value is already subtracted from 95. So, and moreover, when you loop, the very first thing, oh yeah, there's a small error here, there's a small glitch here, I just forgot about this. So if you have observed there, I have again loaded the second element into the accumulator register. That's a small mistake, because I just move this loading value, the loading command here into the loop. So this is not necessary. Actually, this should not be there. It should be here, because only once you're going to load the source index value, and after all, you're just going to subtract the value that is after the your main value. So again, I have to save this file, exit, again MASM subn.asm semicolon, then link subn dot obj semicolon, and af debug subn dot exe. Okay, again I have to load the values. First of all, let us, okay, this time I'm going to load from the section 2. So f8 goes down and 4000, okay, 95, 05, 30, 02, 03, 05, 01, 01. So that's the value. When I go up, F7 and F10, this is 4, and by default I have got the values. The next F7 and F8. Now F1 moved into the SI, 4000 is moved into the SI, CL is loaded, AH is loaded, source index is loaded into AX, and now I'm subtracting 95 minus 5, you get the result of 90. Yeah, I have to show you the values here. So 90. Next, what we are going to get when you execute, so that's borrow the carry flag. You have to observe the carry flag. Since it is 0, there is no change. Then increment si and loop towards the subtract, towards the up variable, not the variable label. So here 90 minus 30, it's going to get 60. Carry flag is 0, so no change in that. Increment si, again loop, and 60 minus 2. Now basically what we think in decimal is that we get a value of 58, right? But here it's not going to be 58, it's going to be 50, sorry, it's 005e, because before 60 it's going to be 5f. So in hexadecimal numbering system, it's going to count like 0 1 2 3 4 5 6 7 8 9 a b c d e f, then 10 11 12 13 14 15 16 17 18 19. In the same manner, when it comes to 50, 51 52 53 54 56 55 56 57 58 59, 5a 5b 5c 5d 5e 5f. After that you're going to get 60. So 60 minus 2, you should get 5e instead of getting 58. So 58, we are going to get that in in regular decimal numbering system, but here we are talking about hexadecimal numbering system. So you have to keep in mind that after the number 9, you are going to get the values a to f. So before 60, you will be having definitely 5e and 5f. So subtracting 2 from 60, will you go 2 steps back. That's why you get 5e. Observe at the AX register. So 5e. In the same case, there is no borrow. Since 5 is less than 6, there is no case of borrow. So carry flag is 0, and you will be moving as without any problem. Again, from here on, observe it carefully. So we have executed, we have subtracted the third element. Now we are going to subtract the fourth element. So going back to the loop, 5e minus 3, 5e minus 3. So 5 steps back from 5e, 5e, 5d, 5c, 5b. So when you execute this particular command, subtract al comma si plus 1, you will be getting 005b in accumulator register. So that's 3 steps. Okay, 3 steps backward. So carry flag is not affected. So no problem. You're going to just execute this. Okay. Now, if I need to show you a step where carry flag, carry flag is affected. So we have done 03, right? Now I need a value which is more than 5b. So let us see the value. I'm going to move into this here, and I'm going to subtract, or I'm going to type here the value 6b. So 6b is greater than 5b. That's a difference of 10, I believe, or 16. Because it is hexadecimal value, you should you calculate that and understand by yourself. That's a small task for you. Now I'm going back to the loop and observe carefully. Already AL is loaded with 5B, and accumulator register is pointing at fourth position of source index, fourth index value of fourth element of source index. But what I'm going to subtract, I'm going to subtract 4 plus 1, that is the element present at fifth position. Now the fifth position, the element is 6B. I've changed it right now. And if you observe, 6b is greater than 5b. Now see, I'm going to subtract here. You get a value of f0, and the carry flag is high. In this case, that means the 5 is not having a value to subtract itself from 6. So it must take a value from here, and then it has to borrow from there. Okay, I will open this in large screen so for better understanding. Unfortunately, my cursor. Oh yeah, I have these commands, up and down commands, right? F7, F7. Yeah, here. So initially, I was having here 5b, and when I have subtracted 6b, b minus b, it's 0. 5 minus 6, it should be 1, but it has gone one step backwards, and the carry flag is 1. So if you execute this command also, it's going to be triple F 0. Triple F 0, because b minus b is 0, 5 minus 6 is not possible. You have to take a borrow from the next adjacent digit, and even that is not possible. So that 0 has to be shifted back to f. Before that, it should take a borrow from the next adjacent digit towards the left side. Even that was 0, but when I subtract ah and double zero, it's all ff. Okay, so in that way it has taken a borrow, and finally you got a value of triple f 0. And now if you go back to the loop, you're going to execute it. You're going to get 0 1 is f. F0, before f0 it should be ef, right? So because e0, e1, e2 up to e9, and then ea, ef, eb, ec, ed, ee, and ef. Finally, after ef you will get f0, and when you're going one step back, definitely you will get ef. Now again, if you do it, so ef will become ee. So again, I have still one count. So I believe, so there is no value, since I have just kept the value as 0 0. That's why it has not subtracted. Finally, FFE is our final value. In order to just confirm you once, what I'm going to do is I'm going to just execute it very quickly with the same values. So I have not typed MASM and all, and when you check the data segment of 4000, it's going to be with the same values. So I have changed this value from 05 to, so after 03 it should be 05, but I have changed it to 6b. So I'm going to again change that value into 05, and I'm going to execute it in a very quick manner. So finally, after the execution of this one, the of course our count value is more, so it's going to execute up to 7. Even it's going to count this one also, and one cycle extra. So the result will be a little bit different. So 90, 30, observe these values and the values that I have typed here simultaneously, so you might get a clear value. So this is 95 minus 5, that gives 90 hexadecimal value. Okay, so 90 hexadecimal is 144 in decimal, so that's what I've typed here. 60, then 5e, I'm here, so I've subtracted 0 2, that means I've subtracted this value. Now I'm going to subtract this one, that's where you get 5b, and then finally you get 56. Okay, actually the program has to stop here, but since I'm having count values more when compared to these values, I've subtracted up to here, so these two will be subtracted. 56 minus 1, 55, and then 54. Even after the execution of this, there is still one more value, that will be this. By default it will be taken this value, because if you see here, when I press F10 for the down, no, it's F8, and when I see press here 4000, so see here it has executed up to this, and the next value is F8, and this is 0. So since there is one more loop, it's going to add this value. Let us type here 0 1. Let us see what will happen. So F1 53, so it was 54, it's 53, and then you have to the program gets out. So that's it for this, and I hope you have understood the addition and subtraction of n numbers using the MASM software. And let's hope we meet in another tutorial for the other program. Thank you.